Tile.
Yes.
Yes.
Which one?
All of
City
them.
of Heroes.
No, not all of them.
Anyway, all right. I need you guys to shut up. All right. So, maximum and minimum, right? Hello. Hello. Anyway, all right. Minimum critical value. So, here's the big point of all this. Take the derivative, set it equals 0.
What?
That's it. That's everything.
That's the
Bam.
oh, so
Notes are over. That's it.
So why do we need this? All this. Why?
Okay, absolute extrema. Okay, absolute. Okay, let f be a function defined on an interval I if there is a number u in the interval for which that f of u is greater than or equal to f of x for all x in I, then f has an absolute maximum at u, and the number f of u is called the absolute maximum value of f of I. That makes sense at all?
Yeah, of course.
Okay, sure. All right. So if there's a number v in for I for which that f of v is less than or equal to f of x for all of x in I, then f has to be an absolute minimum at v, and the number f of v is the absolute minimum of I. These are extrema values. Now, listen. It's the lowest point of your graph.
Yeah, just saying.
The lowest point of your graph. So if that point is lower than all the rest, that guess what? That's the lowest.
Wow.
If that point is the highest out of everything else, that is your
Highest. Maximum. Like.
yeah, that would be the absolute maximum, right? Yeah. We're going to talk about relative also, because we're going to talk about like different things with like wonky curves in the middle, where it's possible to actually have like a little curve in the middle, like an x cubed. Right? An x cubed. There's a local minimum, local maximum. Yes? You guys. All right. Now think about this. Now with your hands right now. You guys ready? We're going to do some interpretive dance. What is x cubed? X cubed. All right, let's try this again. X squared.
Oh, wait.
X squared. Come on. Yes, x squared.
I just remembered. Okay.
Yes, x squared.
X cubed.
Okay, and then x cubed. There we go, x cubed. Okay, one of the sides. Now, if you notice, on an x cubed, absolute maximum should go up to infinity. Absolute minimum goes down to? But there's a little wonky thing that happens in the middle, okay, where you can have a relative maximum, where it's just like a high point, goes back down, then goes back up, okay? That little wonky thing would be a relative to the function. So, here we go. This point right here is the absolute maximum. This point right here is the absolute minimum. Make sense?
Yeah.
Okay, there we go. All right. Local extrema. Okay. Let f be a function defined on some interval I, and let u and v be numbers in I if there is an open interval in I containing u, so that f of u is greater than or equal to f of x for all x in this open interval, then f has a local maximum or relative maximum at u. Then the number f of u is called the local maximum. Now, what does that mean?
Means,
From negative
Try again.
they're not closed, like the dot is not filled.
Dot's not filled, so that would be bracket or parentheses.
Oh.
It's parentheses, very good. Okay, so parentheses, so does it include the endpoints?
No.
No, it does not include the endpoints.
Parentheses means like that.
Square or round?
Round.
Oh, round.
Okay, so right here, there we go. All right, let's keep going. Open, minimum. Okay, here we go. So here's the wonky thing, right? So this is a local.
Is what?
This is a local, okay? It's not the lowest point, but it is a low point. So what do you think that the slope is at that point right there? What do you think the slope of that line is?
U2 minus U.
0.
0. Slope is 0. Okay? It's decreasing, decreasing, decreasing. Then it goes to a certain point. Then all of a sudden it changes to increasing, right? So where my slope goes from decreasing to increasing, that's going to be a minimum. Where a slope goes from increasing to decreasing, at that change should be a, that should be a maximum, right? Basic sense? No, not bad, right? So this could be a local, this could be a local. So these are the points in which that I find that the derivative is going to be equal to 0. Okay? So for these, I'm going to have a couple locals here. So depending on what portion I'm talking about. So, but now if I'm talking about from the interval from A to B, what would my local minimum be? V. What would my local maximum be?
U1,
Just U2.
U. Oh, right.
Because right here, from here to here, what is the maximum?
U.
Yeah, I would only be talking about just this one right here, okay? So, the local maximum means from here to here, the maximum of this interval. This is the minimum right here, a local, for this on here, okay? We're not including the endpoints because we don't have solid dots there. Ah. Find the domain. This should be easy. What's the domain?
Bracket.
Bracket.
One.
Bracket what?
1.
1,
No, not 0.
From -1.
0.
Yeah.
Wait.
What is that?
0 because domain is your left and right.
Just
Your range is your up and down.
3p over
And it goes to what?
3 pi
3 pi.
3 pi over 2. Bracket or parentheses?
bracket.
Why is it a bracket?
Because it's a dot,
It's a
solid dot.
Closed dot, right? Closed dot.
Close that.
Okay? Determine where the function is continuous. Is it continuous from there to there?
From 0 to
It's continuous throughout the.
Yes,
p. It's the
continuous throughout the whole thing. So it's going to be continuous from 0 to 3 pi over 2. Identify the absolute maximum and values in the absolute minimum if they exist. Maximum would be
1.
0, 1.
0, 1.
0, 1. And,
P -1.
and then my minimum is going to be what?
P pi.
Pi.
1.
And -1. Find the domain. Identify any local extreme values. Do we have any weird locals on this one? No. No, we don't have any. Because we only have the highest point and the lowest point. We don't have any weird ones in between, right? No wonkiness. All right, so now on this one, we already did this one. Let's look at this one. What is the highest point here? What's the max?
0.1.
0, 1. What's the min?
2 -7.
Why is it not -1, -7?
Because it's not included.
It's not equal, is it? That's an open dot. All right, what about this one?
The max is infinity.
Nope.
Why?
Okay.
Oh, it's
Wait, what?
Infinity's not a number. Infinity is an idea. It's going up to infinity. It's going up to an asymptote, isn't it? So it's not going to be a maximum here. There is no maximum on this. Okay, but there is a minimum. Where's the minimum?
4, 1.
4, 1. spoilers. I didn't clean my slides. Dang it. 13.
Yeah.
What's the minimum?
No minimum.
No minimum. What's the maximum?
1, 1. It's not really maximum.
Why?
Because isn't the maximum going to be the dot which is close to that one which is not included?
Yep. I'm not gonna have one there, right?
Yeah, because we don't know the coordinates of the.
Yeah, because there is an open dot at E. Open dot at E. So I don't have a maximum, I don't have a minimum. It's an open dot. I need a closed dot to be able to actually say where it's at. Does that make sense?
Yeah.
Yeah, okay, good. Alright, next one is going to be here.
There's a lot of.
Is it continuous over this interval? It's not continuous over the interval. So I can't really say what it would be. So since it's not continuous, I'm like, I'm not gonna get that. But if I were to say my interval would be from 2 to 6, from the interval 2 to 6, I have a maximum at 2, 6. I have a minimum at 6, -2, right?
Yeah.
Yeah.
And from interval from 0 to 2.
Yes. I would have a max at
0, 1.
and a min at,
1, 0.
yeah. Okay. Does that make sense? Does that help you out?
For the little thing.
Yeah.
What was the maximum?
The maximum would be 0, 1.
Okay.
Because 2, 1 is open, isn't it? Yeah. So over here on 15, what do we have? What's our minimum?
No minimum. Yeah.
No minimum because it's open, right?
Yeah.
What about maximum?
You write 2 of them.
I got 2 of them, right?
Negative.
It's on that desk over there.
2, 3.
It's on the big desk.
Oh, I see.
-2, 3, and
2, 3.
2, 3. Okay. Not bad, right? Pretty easy stuff here. If a function is continuous on a closed interval from A to B, then f has an absolute maximum and an absolute minimum on A to B. So it has to be continuous and it has to be closed. That means that I have to include the endpoints. Because whenever I'm doing the math on this, I have to check endpoints. Okay, I have to check endpoints. Yeah. All right, so if function f has a local maximum or local minimum at the number c, then either, okay, this is what we're talking about. Okay, either f prime of c is equal to 0 or f prime of c does not exist. Soak that one in. Now, f prime of c. What would I have issues with f prime of c not existing?
Because there's not close.
No. No, it's going to be closed.
But there's no slope.
There's no slope there, right? Okay, that would be a pointy point, right? That'd be a pointy point. So that would mean that I would not have a derivative at that point, right?
Or it's just a line.
No, that's a slope of 0, right?
Oh,
Okay, slope is 0. And what about, let's say, a half circle? Or even better, just a whole circle. So imagine in your mind a whole circle.
yeah.
So what is the slope of the top and the bottom? 0, very good. The slope is 0 on the top and bottom. What is the slope on the left and right?
There's nothing. It's all. I mean, it's going straight up. I don't know what the slope of that would be. It's a
Okay,
lot.
what slope? Slope is always rise over run, right? So would I have rise?
Yeah.
Okay, but what would my run be?
0.
0.
1 over 0.
1 over 0. What is 1 over 0?
There's obviously.
Undefined. That's what we're looking for. Undefined. So we can actually find, there's going to be some problems later on that you're going to actually have to find, okay, a vertical tangent. So to find a vertical tangent, that just means that your slope has to be undefined. Okay, you're going to eventually actually be able to do that. So we're going to find right now slopes of 0, which is going to be my top and bottom of that imaginary circle. And we're also going to do slopes of undefined to figure out where the tangent line would be vertical. Okay, that would be another answer where it does not exist. Okay, the function could exist, but that does not. All right, if a differentiable function has a local maximum or a local minimum at C, then f prime of C is equal to 0. That's what I was just saying right now. My derivative is equal to 0. Min or max, derivative equal to 0. I know, spoiler alert. Okay.
Just need to stop. Spoiler.
A critical number of a function is f is a number C in the domain of f for either f prime of C is equal to 0 or f prime of C does not exist. So where does it not exist?
Add x
Doesn't exist there, right?
to x4.
Okay, now that's referred to as a pointy point or a kink. A kink. Kink. Okay, you're not going to get a slope off of that because that is pointy. If you try and balance it on a point, it's not going to work. Okay, it's not a gradual change. It's not a gradual change. So it keeps going. You just have a slope one thing on one side, slope on the other side is not the same. So it's not a gradual change from there. Okay, so it's kind of like, you know, having the absolute value function. Absolute value function is going to look like this, right? So right here, I have a slope going down here, and then it changes to go up this way. So that means that that's not going to have a slope on that one. Okay, just at that point. But the left side has a slope and the right side has a slope, but right at the very center, f prime of 0 is not going to exist there. I'm sorry, f prime of C is not going to exist there. All right, so let's take a look. Also, not going to exist here. Same issue. No. Haha. There we go. Find any critical number for these following functions. So this is going to be the last problem I'm actually going to do with you, because I want you guys to start and work on this. All right, let's see. So first thing I should do is f that. Right? We want to f that. So if I f that, I get
That's 3x squared minus 12x plus 9.
right.
It's equal to 0.
Okay, f that now, right? So I took the derivative, now f it, right? So factor it. What do we get? I'm going to take out a 3 quantity. What's that? X squared minus 4x plus 3. Now, the factoring tricks.
-1 and
Okay, there's some tricks on this, and I'm going to go over these tricks real quick because some people haven't had this in a while.
that's when the left and right, sum of left and right equals to the middle coefficient.
Not really. All right, watch this.
What's the rule like this?
Is there a plus sign over here?
Yes.
Is there a minus sign right here?
Yes.
All right, when you're multiplying, how do you get a positive?
Positive.
Positive, positive. What else?
Negative.
Negative, negative. So, if you have a positive here, that means you have to have a positive, positive, and a negative, negative.
But we have a negative.
And right here, because this one right here is negative, that means you have two negatives, right?
Yeah.
We have two negatives. All right, so now let's think about this. What two numbers multiply to be positive 3 that add together to be negative 4?
-1, -3.
Very good, -1, -3, right? So it's going to be 3 quantity x minus 1, x minus 3.
Yeah.
And then what did I say to do with that?
Equal to 0.
Set it equals 0. Very good. We got the derivative equals 0. So what's going to happen to that 3?
You can
If I divide both sides by 3, what happens?
It'll be still 0, like we can just.
Yeah, it just goes away, right? It just goes away, because I have no x that's got factored out here. So I'm not going to have anything to do with the 3. I just simplified everything. Okay, so now because of that, I'm going to have a factor using zero product that each one of these, so it's going to be x equals 1 and x equals 3. There's critical numbers.
Can't you use the rule, like if you sum the last and right coefficient of equals to the middle one, so the x1
Yeah.
is equals
Yeah, that's
1
what I did.
and x2 is
But yes.
c over
Yes.
a.
Yes.
That's-
Yes.
Okay.
Yes. When we have to factor a bigger one, I'll actually do more with that. Okay? But that's just the basic of that one. Make sense? Okay, let's do. Okay, how would I do B? I'm not going to do B, but how would I do that? What rule could I use for that? Quotient, right? Quotient. So now what's the derivative of 1 though? 0. So that's going to help out my quotient rule a whole lot, isn't it?
Yeah.
Because anything times 0 is 0.
Yeah.
Okay, so that you guys could actually do that too. All right, so I'm going to do C though. Okay, I'm going to skip B and go to C. That one's a good quotient rule because both of them actually have a value. And that one has a quotient and a chain. So, let's see. So if I call this one F and I call this one G, so let's see, F prime would be what?
2 over 3.
2 over 3.
Minus 2 to the negative 1 over 3.
Yep. 2 over 3 quantity x minus 2 to the negative 1 over 3, because I subtracted 3 over 3, right? And what's the derivative on the inside? 1, right? So that's not going to change that. Okay, so G prime.
1.
Yes? So let's quotient rule. F prime G, so it's going to be 2 over 3 quantity x minus 2 negative 1 over 3 times G, which is just x, minus G prime, which is 1 times, that's weird, 1 times x minus 2
You like this board, right?
I know. I think it's on its last leg already. It's only 2 years old, but it was broken when they installed it.
Ask
Okay.
for a new one.
And what am I still missing?
Divided by x.
All over what?
X squared.
G squared, so that's x squared there. Very good.
You can subtract the x minus 3.
I could do a lot here, but I'm not going to do anything
Because we're
yet because I could clean up a whole lot. I love this part right here. Set it equal to. That is the derivative, right? Set it equal to 0, right? So if I set it equal to 0, what's going to happen to my bottom?
It can be.
Okay, so all this is going to be equal to 0. Let me move that here. All that is equal to 0, right? Since it's all equal to 0, can I multiply both sides by x squared?
But we need first to say that x squared is not going to be equal to 0.
Okay, we already know that because why?
Because 0 can be on the bottom.
Now, look at my function g in the first place, little g.
Ah, it's not.
Can I have 0 in my denominator? Can x ever be 0?
No.
No, because right there, that's gonna give me 0 in the denominator, which what's gonna make my whole thing undefined, right? So guess what? Isn't that a critical number too? That's pretty critical.
Wait, I'm
It-
sorry, mister, what is it?
Critical numbers are where my derivative is equal to 0. That's gonna be my minimum, my maximums, or my asymptotes, or where it cannot be.
Oh, okay, so
Okay.
there's numbers that you're looking for.
Yeah, so all the things that are gonna be helpful for these things.
Gotcha.
Okay, so now, if I multiply both sides by x squared, what's gonna happen?
The X
Get rid
squared
of
goes
the
away.
X squared goes away, doesn't it?
Yeah.
Yeah, that's gonna help me out. That's why I love doing that. Okay, if I have a fraction, I can clear that whole thing out. So that goes away, but now, I need common denominators here, don't I? Yes? So I'm gonna multiply this side right here, okay, top and bottom by 3 quantity x minus 2 to the 1/3. But when I do that, what's gonna happen here? It's the same thing, that x minus 2, x minus 2. What's gonna happen with that 1/3? The 1/3 and the 2/3. If you multiply, what do you do with your exponents? You add them, right? If you're multiplying, you add the exponents. If it's x squared times x to the 3rd, it's x to the 5th. Okay? So you add the exponents. So again, we're gonna end up doing that. So it's gonna be times 3 x minus 2 to the 1/3.
Isn't it negative 1/3?
No, because I moved it to the denominator for this reason. So it was negative up here, but if you notice, I changed it here, right? So the 2's on top, the x should also be on top, the 3 is on the bottom, because that was the bottom denominator of my fraction, right? And the negative exponent can move the whole thing down to the denominator. Okay? All right, so now that I'm doing that, it's going to be the same top and bottom. Same top and bottom here. So now I could actually have common denominator here. So I'm going to rewrite this. 0 equals 2x. Now it's going to be minus 3 quantity, because like I said, you add your exponents, so it's going to be 3/3, which is just 1, right? X minus 2 all over 3 quantity x minus 2 to the 1/3, right? Because that's going to be my common denominator again, right? So getting fractions over fractions, kind of a pain, but it works. Now what's going to happen to that bottom now?
We said it's not equal to.
Set it equals 0 again, right? Set it equals 0. So let's do that. Set it equals 0. So if I do that, multiply both sides by 3x minus 2 to the 1/3, and when it's times 0 on the left, it goes away. So now I'm going to be 0 equals 2x minus, and I'm going to distribute that. So it's going to be 0 equals 2x minus 3 quantity. Is it x minus 2, right? Yes? Just double checking. All right, good. So, because I have to distribute. So 0 equals 2x minus 3x minus 6, or plus 6, sorry. Okay, so now I get 0 equals negative x plus 6, so x equals 6.
Yes.
So x equals 6 is one of my critical numbers. So that's going to place in which it's going to be minimum, maximum, okay, something there. Okay, something there. And I also know what? I cannot have 0, right?
Yeah.
X cannot be 0 because that's going to give me 0 in denominator of my function. So the domain
And it's,
has a hole right there at 0.
and at 2.
And at what?
And at number 2.
At number 2.
Because before we divided it all by 3.
Hold on.
Here,
That's where I was getting at.
we multiplied it by 3x minus
Now,
2 to the 1.
take a look. Can I have that?
Yes.
Okay. Can I have that? Look at my function and now look at my derivative.
Like you can have 2 in function, but like if we will place 2 in this last one which we wrote, it will be 0 on the bottom.
Okay, so at that last part right there, you're saying I can't have 2?
Yeah, because it can be 0.
Okay, but that's... Can we test that? How can we test that? Let's see.
Yeah, just grab.
Let's see what we have. Because that was actually the point where I was going to get to next anyway. Oh, wow. For those people watching the video, you got something interesting right there. All right. All right, so my function was what?
Your function was x minus 2 to 2
X
thirds.
minus 2, close, raised to 2 over 3, right?
Yeah, divided by x.
And over x.
Over x.
There we go. Hit enter. We got something here at 2. Can I check that? So right now we know it can't be equal to 0, right?
It's the point 2.
Okay. Let's see. We have the point 2. Let's see. Menu, trace, graph. Let's see. What happens at 2?
It's 0.
So does it exist at 2?
Yeah,
It does.
on the graph. No, I know it's existed. I mean.
Thank you. All right. So it does.
Yeah.
Okay. Now I'm going to show you guys. Let's go ahead and let's graph the derivative
Yeah,
too.
that's what I was saying.
Let's graph the derivative.
Okay.
Okay, so now these are all slopes, so don't confuse yourself here. So what is my first one? So it's going to be 2/3, right?
Yeah, 2/3 x.
Control, divide. So on top it's going to be 2 over 3, and it's x, so parentheses, x minus 2, close, raised to negative 1 over 3, right?
X.
Times
X
x,
minus 2 to the 2/3.
okay, then it's going to be x minus 2 to the
2/3.
2 over 3
And divided obviously over x.
x squared, right? There we go.
Here it's not existing at 2. That's what I said.
You're saying that the derivative does not equal there, right?
Yeah.
Okay. So the derivative does not. So we're going to get more into that when we have our second derivative too. So the graph does exist, but the derivative does not at 2. So yes, that would be a critical number of that. So, and now, what did we come up with here? So we said that right here at 2, 3, 4, 5, 6, this is the point where my slope is equal to 0, isn't it?
Yeah.
Yes. My slope is equal to 0 here. And then 2 is going to be undefined for this. Alright, so,
And undefined for 0.
yes. Does that make sense? Are we okay on this? This is, you know, some complicated stuff, but I want to give you guys, we're really not going to have time for the work, but we will be able to work some more in class on Tuesday. Alright? So, don't forget everyone, like and subscribe, right?